where we left off last time is this realization that the simple sets we've come to know and love, the ones that we can represent with automata or regular expressions, there's a lot of them, right? We've seen tons and tons of examples, but they're not by any stretch of the imagination the full picture. So there are lots of sets that seem pretty okay, like A to the n, B to the n, or like palindromes that seem to have some nice internal structure but aren't regular. All right, so we spent a bunch of time last week thinking about what it means for a set not to be regular and how do we prove that, say, with the pumping lemma. But if we want to go past that, if the goal of the class as a whole is to try to get us a picture of computers as we know them, then the little automata that we've been dealing with so far are clearly inadequate. They're clearly only telling us a small piece of the picture because there's all of these fairly simple sets that aren't representable with automata. And so these automata are very limited in that they can't count. They couldn't count how many characters we had at the beginning to match the number of characters we had at the end. They can only remember a bounded amount into the past, and they can't backtrack. When we think of a machine processing a string, we think of the string being given to us one symbol at a time from left to right, and once we've processed a string, we never go back and look at it again. So all of these feel a little different from the programs that we typically write when we're writing in, say, Java, Python, whatever your favorite language is. So we know computers are more powerful than this model, and as we try to expand our formal theory to match reality or approximate reality, we need to relax some of the conditions that we see in automata. So the model that we're going to work with in Chapter 2 does that. And the idea here is that we allow some memory of unbounded size. Okay? In automata, DFA, NFA, our only memory was the state that we were in. We often associated with them some sort of like an abbreviation, an idea of what amount of the string we've seen so far, what features they incorporate. That's our only way of remembering stuff about the string that we've seen. And there's only finitely many states, and we spell them out at the beginning, and that diagram doesn't change. So in our new model, we're going to allow some part of our memory to perhaps change over time as we're processing strings. And so we've got this generalization of our finite automata called push-down automata. What we'll see is that it turns out that there's an equivalent way of generalizing regular expressions. That's called context-free grammars. So push-down automata is where we'll start with. This is section 2.2 in the book. And then we'll go back to section 2.1 for context-free grammars. Just the delta that we need to do, the difference that we need to do between NFA and push-down automata is smaller than the change that we'll have to do to get to context-free grammars. So I think in terms of learning and building on what we know, getting to push-down automata first will be easier.